Alright folks, welcome to another video on motor controls here. And so this is actually a continuation of what we have been discussing so far, and this will be a very short video because we are presenting another technique to model PMSM and FOC control using another set of tools. So we are basically implementing the Stator reference frame model of a PMSM that we discussed last time, and we're using MATLAB's simPower Toolbox. MATLAB's simPower Toolbox for the implementation here, and this this might not be available to most of you, but if you do get the software through a university, you may have access to this piece of software, or part of this software from MATLAB, which makes your life a lot more easier. And let me show you where to find this toolbox and at least see if you have it. So if you go into your Simulink browser here, library browser, you can try to find this in Simscape. Okay, so in Simscape, so again you have to purchase this separately, and then if you go to specialized technology under, let me see, I think it's Simscape, specialized technology, and right here. Okay, so under specialized technology and under fundamental blocks, so these blocks have especially they're very simply implemented, and it makes it easier for the user to implement a complex model like a PMSM. So you have a lot of different blocks that are needed for power systems, especially if you look at this mutual inductance block is one of the primary components that is going to help us implement this motor model. So it would, I would recommend you to see if you have it. If you have a student license, you might be able to get this for a very small cost, like $10–20. So I recommend you get that. It will be very easy for you to implement these kind of models, and they run relatively fast compared to other models. Like the MATLAB equation-based models, or compared to those models, the simPower blocks, simPower-based models run much faster. And then this also has the additional advantage of having different power electronics components. So if you look here under the power electronics, you have a lot of different elements which can help you build an inverter to control this model, which will be a later discussion for us. But here we're going to be looking at the FOC, or field-oriented control, and the permanent magnet synchronous machine modeling only. We'll add the inverter stage next. Okay, so here when you look at this, this is basically what we have seen in the last video. You have the ABC motor equations here in the bottom, so I'm just using that for comparison. But here on the top, all the same high-level blocks, we have our position signal generation here, and then the only difference you're going to see here is this block, right? This where we implement the model, the motor model. Everything else is the same. And once we go inside this, you'll see that we have a couple of different elements here that are being used. So this is a controlled voltage source. This is what is acting as our inverter in this case. It's a linear inverter that we are representing. No switching, so you don't see any PWM in this case. And then those voltages pass or are fed to these inductors, or in this the mutual inductance block, which also contains the resistive element. If you'd like, you can set the resistive elements to 0 and then add external resistors, just so that you can get a visual understanding. And then the second set of voltage sources represent the back EMF. Okay, so I'm generating the back EMF basically based on speed and this theta E. If you go back into our stator reference frame voltage equations, you will see that we have a back EMF component which is proportional to the speed and then your flux linkage coefficient here, and that is basically constructed based on these formulas. Okay, so specifically if you look at the back EMF, it's in the stator reference frame, they are a function of theta. Okay, they are a function of theta, and then we are setting the amplitude based on the flux linkage coefficient and your lambda m. Okay, if you'd like, you could code the lambda and the speed, the product, the amplitude calculation yourself in here. I chose to do it differently. I chose to have it externally calculated and then fed in. It doesn't make a difference. And then those values are getting converted to these physical, what MATLAB calls a physical signal, through these sources, controlled sources. And now these construct the electrical circuit here. Okay, and then if you go inside the inductance block, you'll see I have a matrix representing my inductance because I have 3 voltages and 3 currents. So this is a 3 by 3 matrix. And I also have 3 resistance values. So I have a 3 by 3 matrix with the diagonal elements representing the resistance. Okay, so this actually makes up my model, and then you can actually directly measure the currents flowing in this circuit using a current measurement here. Okay, so this is similar to a phase current measurement, and those phase currents are fed outside our block for our field-oriented control approach. Okay, so pretty close to what you see in a real-life application. And one big factor here is this power GUI block. When you build a model like this using simPower, every time you will need to include this power GUI model, power GUI block, and this is actually included with the simPower toolbox or SimScape toolbox. Another important fact I want to mention here is this neutral point. Okay, so adding this neutral helps solve these equations. Sometimes I've seen the model throw out an error because it's having trouble finding a 0 location. So I would throw in this neutral point either here, or you can throw it in here. Doesn't make a big difference. And that's basically it. So you have your voltage fed in to your circuit, to your motor. You have your inductance and resistance elements here. You have your back EMF terms here. Okay, and then we have our current measurements here, because this is where the current's flowing, right? The currents flow through the inductors, and that's basically it. So it makes it very convenient to build a model. You don't have to write equations or do calculations like we did in this previous model. Okay, it was still easy enough, but you can get away with that aspect too if you are interested in, if you would like to use this model. And this can also help some modifications to your motor very easy. Okay, and yeah, so once you have all this set up, we can run this model, and you can see that the reason it takes a little longer because we still have this original model, the stator reference frame model here. Otherwise it would run much faster, not significantly faster, but and then if we compare the waveforms, you'll see that they are almost the same. Okay, they are very much the same. You can see the yellow is the first one, blue is the second model. So that's our Q-axis current, and then we have our D-axis current showing a similar response here. Okay, it's showing a similar response with slight difference. I mean, that's acceptable. But yeah, so you have a good representation of the PMSM model using the simPower toolbox. Okay, so that's the discussion for today. So next time we're going to be looking at the inverter. How can we add the inverter here into this model, followed by another short video on how you can build the dyno setup, right, with all the inertia and all that, to wrap up this sequence of videos. All right, folks, I hope you enjoyed. I'm going to wrap this up. Please let me know if you have any further questions. Thank you.